Good day, my name is Thesis and I will be talking about my thesis work, which is about simulating and repairing autonomous driving systems using recorded traffic data. So first I'll give a short overview. I'm gonna introduce some of the concepts that I'm using in my thesis. Some of these are, for instance, autonomous driving systems, simulators, rule sets, automated repair. These are things that I'll go into more detail later. I'll go over the approach that I've taken in this work. I will explain and showcase the design of my study, which includes the research questions that I'm posing, and I will explain the two case studies that I've created. And finally, I will close off by talking about the future work that I would like to do before finishing my thesis. Alright, so let's talk about autonomous driving systems. So an autonomous driving system is basically a system that is able to drive a vehicle without human intervention. Now it can be all kinds of vehicles. It can be a drone, it can be a boat, but in the case of my thesis I'm talking about a car. You can see an example of a self-driving car on the right. So it's equipped with all kinds of sensors which is able to sense its environment. And an autonomous driving system, it usually consists of several modules, and these modules are all responsible for different tasks. So for instance, on the right, I've shown four of the main modules. First one is the sensing module. It gathers sensor data, gives this data to the perception module, which then processes and abstracts this sensor data, and it processes it into information. This information is then used by the planning module, which will look at this information about its surroundings and decide what action to take. And this action is then given to the control module, which will try to realize it. Now the focus in my thesis is mostly on the planning module. And obviously with self-driving cars, real-world testing can be quite unsafe, and it's also quite expensive. You know, if you crash your car, it can cost a lot of money. So that's where simulators come in. Alright, so simulators are basically used to safely test autonomous driving systems. And they do this by simulating the actual driving environment. So usually these are highly detailed 3D environments, and they have roads, they have realistic traffic, so like cars, bicycles, pedestrians walking on the sidewalks. They may have some weather conditions like rain or snow, which can adversely affect the way some of the perception modules work. And they often have physics simulations to simulate all the physical components of vehicles, like wheels, and also to simulate friction on roads, etc. So often these simulators, they can simulate sensors like cameras or LiDAR. And these, can be used to then test an autonomous driving system from really the front, so the lowest level, the sensor level, to the actual planning level, where you have this software making choices based on all the data it's received from its environment. Now there's two main simulators that are most used in research. First one is AirSim. It's created by Microsoft, and the second one is Carla, which is created by the Computer Vision Center. And they're both quite similar in their capabilities, but there's obviously some small differences. I think the biggest one is that AirSim is able to simulate drones as well, autonomous drones. So let's talk about rule sets next. So rule sets are a component of a rule-based autonomous driving system, where the rule set is part of the decision module. So a rule set will allow a decision module to prioritize the outputs of different modules. So what does that mean? Well, we have an autonomous driving system. You have multiple modules, and these modules might give some conflicting outputs. So for instance, let's say if we look at the example on the right, we have two modules. We have the adaptive cruise control module and we have the pedestrian protection module. And the adaptive cruise control module doesn't detect any car in front of it, which is what it's supposed to do. And so the adaptive cruise control module will say, okay, let's accelerate. But the pedestrian protection module is, of course, used to detect if there's pedestrians around the vehicle. And in this case, there's 2 pedestrians walking on the sidewalk. So the pedestrian protection module will obviously say that the car should brake. Now, which of the 2 modules should you believe, right? Which output should you take? And this is where the rule set comes in. So it introduces priority rules for these 2 modules. So in this case, there would be a rule. That's basically the top rule here, which is whether a pedestrian is detected. And in the case of no pedestrian detected, we can of course, take the output of the adaptive cruise control. But if there is a pedestrian detected, then of course we should brake and follow the output of the pedestrian protection module. Now these rule sets, these are often created by domain experts because they can become very large and very complex. And obviously if there is a fault in them, if there is a mistake, then that could lead to very severe consequences. And so this is where automated repair comes in to find these faults, these mistakes in these rule sets, and solve these, I call them feature interaction failures. So when these 2 features, these 2 modules interact and causes a failure, it can fix those problems. Alright, so let's look at an automated repair algorithm. So in this case, we're looking at ARIAL, which stands for Automated Repair of Integration Rules. Its input is a faulty rule set and a test suite. So a test suite is basically a collection of driving scenarios. And it's basically a search algorithm which mutates the rule set until one of the mutants passes all the tests in the test suite. Then there are safety requirements that determine the severity of the failures, which is basically the fitness of each mutant, so each mutant rule set. And fault localization is used to pick suspicious statements or rules at the moment of failure when executing the mutant or rule set on the test suite. So if we look at the pseudocode of ARIAL, you can see that it begins by initializing the elitist archive. It will then evaluate the original faulty rule set and record its fitness values, then adds it to the archive. And while any mutant in the archive is not satisfying all the test cases in the test suite, so not passing all of them, what will happen is it will randomly select a parent from the archive. It will then generate from this parent rule set, it will generate a patch, so a mutant rule set. And it does this by either modifying the rules or by shifting the rules up or down. It will then evaluate this mutant on the entire test suite. And finally it will update the archive with this mutant and its result. And it does this until there is at least one test case that passes all the test cases in the test suite. Alright, so now that I've given an introduction of all the different concepts that I'm using in my thesis, I want to give you a small overview of the approach that I'm taking. So this is a diagram which shows basically the entire architecture of all the systems that are introduced in my work, but I'll just walk through it on a high level. So AutoTest is my simulator, the simulator that I've built, and it takes in data from a very large traffic data set. Then AutoDrive is the autonomous driving system, which is rule-based, so it uses a rule set which is able to be run on the AutoTest benchmark, so the AutoTest simulator. Then AutoRepair is a variation of ARIAL, which is the automated repair algorithm that I just introduced. And this will be able to patch the rule set based on the the feedback it receives from the simulator. And then AutoMatch is a necessary step or necessary algorithm that I had to create in order to use the data from this data set. And AutoMatch, it basically allows me to map a trajectory from an agent on a road network and map it to a route that it has taken. This is not a trivial thing. But yeah, I hope it's a little bit of an overview, and I'll move on to the next slide. So I'm going to go into a little bit more detail on AutoTest. And AutoTest is a simplified simulator. So in the introduction I talked about Carla and AirSim, and these are some very highly detailed 3D simulators, 3D driving environment simulators. And these obviously have quite a bit of overhead, considering that the graphical computation cost is quite high. And so since this dataset that I'm using has a lot of different scenes, a lot of different driving scenarios, I needed something that was lightweight. And since I'm also focusing mostly on the planning module, the graphical fidelity and the way the sensor and the perception module work, it's not important. I can assume that those are working correctly and focus on the planning module, the rule set. So AutoTest is a 2D top-down simulator, so it has top-down driving scenes. Agents are represented as 2D bounding boxes, and a so-called kinematic bicycle model is used for realistic driving physics. This model has been used in a lot of self-driving research, and it's quite a realistic and accurate depiction of a vehicle or car driving. And it uses, so AutoTest, it works very well, and it uses the Woven Planets Level 5 prediction dataset, which is about 1,000 hours of recorded traffic data. And this data is, or these hours are split into 170,000 scenes of 30 seconds each. And so what AutoTest does is it will take this raw scene data from the dataset. It will load it into a so-called scene and map loader, which will abstract it into a scene. I've explained it here in a bit more detail. So a scene consists of a number of agents and an ego vehicle. The ego is the self-driving vehicle, and these all have some properties, ID, position, yaw, velocity, and the route. It will abstract the map, so the road network, and it will record for each lane the ID, its speed limit, what kind of turn type it is, all kinds of relevant information for the self-driving vehicle. And finally, it will record whether there's any active traffic lights in the scene. And it then passes all of this on to the simulator, which can then take autonomous driving systems to run on the scene and to determine what kind of decisions this automated driving system will make. So scene prioritization is something that's quite useful for reducing the amount of test cases that you want to run in a certain test suite. And in my case, I've introduced scene prioritization based on diversity and execution cost. So diversity is given by a combined metric where for each scene I have extracted some important features, like the distance, the direct distance between start and end of the self-driving vehicle in the recorded data. The road distance, so that's the distance of the roads that's been traveled. The number of left turns, right turns, and you can go on. So this extracts some interesting information about the trajectory of the car that you're looking at. And we're using a evolutionary algorithm called MOSTC prioritizer. And what this does is it will mutate an individual, where an individual's genes is the execution order of test cases. So for instance, this individual parent 1 has genes in order of 1, 2, 3, 4. So that means that if you want to execute this individual, you would start by executing the first test case, and the second, and the third, and the fourth. And what the algorithm tries to do is to maximize diversity between neighboring tests in the execution order. So it will try to maximize diversity between the first and the second position in the order, for instance, and the second and the third, etc. And it will minimize the execution cost to prioritize the least expensive test cases. So it's desired to have less expensive, so less expensive to run test cases, at the front of the order. So here I have a small example of what a potential crossover might look like in this evolutionary algorithm. I have two parents. They have two different sets of genes, and they have different levels of diversity and execution cost. And what happens is that the genes are then combined. In this case, it was a single point crossover. It can be other crossover operators as well. But here it's chosen to pick the first two genes of the first parent and the second two genes of the second parent. And this gives a new sort of gene set. And when we calculate its diversity, we actually find that it has a lower diversity. And when we calculate its execution cost, and there are metrics for this, it is also lower than its parents. So this would be an offspring that would be sort of a successful mutation. Okay, so now I'm going to move on to AutoDrive, which is my rule-based implementation of an autonomous driving system, which has 5 modules. It has the rule set, which is basically the planning module, the decision module. There's different names for it. There is the adaptive cruise control module, automated emergency braking, traffic light management, and navigation. Now, adaptive cruise control, the braking and traffic light management, these are longitudinal modules. So these are modules that are responsible for movement in the longitudinal axis. So if you have a car, it would be the axis that's pointing ahead. And lateral means that navigation, for instance, is responsible for movement in the lateral axis. So that's the axis that's pointing to the side of the car. And then the rule set, in the case of AutoDrive, it will decide or prioritize the outputs given by these longitudinal modules. And every module will give an acceleration output. So adaptive cruise control may give an acceleration output of go ahead with 4 meter per second squared, while emergency braking might say, okay, let's brake max braking acceleration. And so the rule set decides between these outputs, and it will feed this information to the AutoTest benchmark, and then you will receive information from the AutoTest benchmark on what the next position would be based on your current output, and then you will basically look at the whole scene again, plan around it, decide the right output to take, and give it to the benchmark again. It will sort of create a little simulation loop. And this basically sums up the AutoDrive module. It's quite simple, it's quite effective. It's not a very large rule set, but it definitely does the job. Alright, so let's take a look at AutoRepair. So AutoRepair is my variation of Ariel, which is the automated repair algorithm that I've introduced. And I'll show you quickly how it fits into the whole picture. So AutoRepair, it will take as input a faulty version of AutoDrive, and it will feed this to AutoTest. It will run it on AutoTest, and AutoTest will give this version of AutoDrive a fitness value. Then AutoRepair will try to mutate the rule set of AutoDrive and create a mutant that is then again run on AutoTest. It gives a fitness back, and it does this process just like Ariel, trying to find a patch that is able to pass all test cases. Now the difference is that I've added a new modify mutation operator. So Arial actually has two different types of operators, the shift and the modification types. So shift just reorganizes the rules, so it moves them up or down, or swaps some rules. Whereas the modify operator will actually modify some of the rules themselves. But my modify mutation operator is actually going to try to modify some of the individual modules. So not just the rule set, but modules that are within the rule set. And what it does is it will select a random module that's been that's inside of a selected statement that's been found by a fault localization, and it will then mutate these module parameters. And so this would allow for repairs of some module specific faults that normally cannot be fixed with Arial. So let's look at an example. So here we have the adaptive cruise control module. Let's say that it has two parameters, a trading time of 3 seconds. So the trading time is the time that it should have in front of the car that's in front of the ego car, and a minimum trading distance of 5 meters. So if we modify it with this new mutation operator, it will change one of the parameters in a way that modifies it such that it will be different. And in this case, it has modified the trading time to become 4.5 seconds instead of 3. And then when we run it on AutoTest, it's going to give some different results. And hopefully this can lead to some repairs of module specific faults. So the final part of the approach that I want to talk about is the algorithm called AutoMatch. So this might seem a little bit out of nowhere, but AutoMatch is actually quite an essential piece of my thesis, which is used to actually map match trajectories from the prediction data set. So this traffic data sets, which has hundreds of thousands of agent trajectories, and it matches these trajectories to a lane level road network, and it will output a route. So this problem of detecting what lane an agent is driving on is not trivial, and the solution for this are lane level map matching algorithms. Typically, the input is a GPS trajectory and a lane level road network, and the output is a feasible route. Now, AutoMatch is special in that it's one of the only lane level map matchers that exist. It's quite a new field of research, and it can quite effectively handle gaps in a road network. So when a road network is not correctly made, or some faults in the connectivity, you can imagine that if you have let's look at this example here. We have a lane here. All these little blocks are lanes. If usually there should be a reference from this lane to the next, so that that okay, what are the next lanes when I'm on here? That would be this one. But sometimes there are faults in the road network, and especially in the size that I'm using in my thesis, a road network of, I believe, 6,000 lanes. And when you have this, you want your map matching algorithm not to get stuck, or to not be able to compute the actual route. So AutoMatch is actually able to do this. What it's also able to do is it's able to deal with trajectories, or part of the trajectory that goes off-road. So this is also typically something that can cause a problem. If you go off-road, you don't know what lane you're driving on, and the map matching algorithm won't work. But AutoMatch will be able to detect this, and will still accurately find the corresponding route. So let's move on to the study design, and I'll start by posing the two main research questions, and I'll start with the first one. So the first one is, how does AutoMatch compare to the hidden Markov model map matching algorithm when matching GPS level trajectories to a lane level network in terms of correctness or efficiency? And I'll get into more detail about the hidden Markov model map matching algorithm. But I'll go to the second research questions. So, what are the trade-offs between AutoRepair and Aerial when applying it on a rule-based autonomous driving system with varying amounts of and types of faults within the AutoTest benchmark in terms of effectiveness and efficiency? Alright, so let's talk about the first case study, which is created to try and answer the first research question. So, we will be comparing AutoMatch to a suitable baseline, and in this case I've chosen the hidden Markov model with the Viterbi algorithm. So this has actually been used a long time ago, and it was one of the first map matching algorithms that was released, and it has recently been modified to also solve for the lane level map matching problem. So this is quite a popular and suitable baseline. Then the trajectory of the most diverse scenes, so the 50 most diverse scenes of the AutoTest benchmark, will be used as the trajectories to be map matched with. And I will be measuring the performance using 3 performance metrics. Recall and path length error are used to prove correctness, so that will answer research question 1.1. And the execution time is meant to answer the research question 1.2 for the efficiency. So if we look at a small example, here is a trajectory which has been map matched by an algorithm to create this estimated route. Then there is this ground truth route, which is actually a straight line. If we want to calculate the recall, it's simply the amount of correctly estimated lanes in the route divided by the total amount of lanes in the ground truth route, right? The path length error is defined as the amount of wrongly added length of lane. So the wrongly added length of lane in this case would be this detour, plus the amount of wrongly subtracted length of lane. So the wrongly subtracted length of lane would be this little piece here, because it's present in the ground truth, but it's not present here. And that's divided by the total length of the ground truth plus the amount of wrongly subtracted length of lane. So that concludes our first study. Now we're going to look at the second case study. In this case, we're going to be studying AutoRepair, and we're going to be comparing it with Aerial, since they're so closely related. Now the benchmark on which we'll be doing this comparison is of course AutoTest. So we're going to be using the 5,000 most diverse scenes as a test suite. And these scenes are, the result of this scene prioritization, which I talked about previously. And we're going to take AutoDrive's original rule set, and we're going to artificially introduce faults. So here is the pseudocode of the original rule set. So we have 2 statements here. We have the whether the time to collision is less than the stopping time, then we should do automated emergency braking. Otherwise, if the relevant traffic light color is red, then we need to do traffic light handling management. And otherwise, if there's nothing like that, we're just gonna do some adaptive cruise control with the trading time, which is a parameter. So we're gonna introduce at most 2 faults with all possible combinations of faults. So we're gonna exhaust all kinds of faults. So I've included a list of or table of different kinds of faults. So here I've added some. First type fault, rule ordering. So in the original code, it would be the original rule ordering, and then in the faulty code, we would swap the order of 2 rules. We would swap these 2. Then another fault type could be the relational operator direction. So for instance, if we have the statement of the time to collision is less than the stopping time, if we want to make it faulty, we just swap, invert the direction and make it larger than the stopping time. Same goes for equal signs. We can make it not equals. Then we have the fault type for the threshold value. So let's say that the stopping time is 2 seconds. In the faulty code, we can modify it, mutate it to something like 0.5 seconds. You can imagine that that could cause some faults in the execution of the test suite. And then finally, to test for fault in a feature, we're gonna change the parameters of a module. So feature is also for a module. In the original code, we may have the training time of the adaptive cruise control at 3 seconds. So cruise control at 3 seconds. In the faulty code, we might put it to 1 second. So that would mean that the car is only keeping a 1 second safe distance from the car in front of it. Now, that doesn't sound very safe. So that's how we would introduce faults. So in order to actually compare these two repair algorithms, we will use two performance metrics. The first one is the number of failing test cases, which is used to answer the research questions 2.1, which will try to determine the effectiveness or compare effectiveness between AutoRepair and Ariel. And the second performance metric will be the time to repair. And this is meant to answer the second research question, the second sub-questions, namely for efficiency, comparing efficiency. So one of the things about these automated repair algorithms is that they both contain randomness. And in order to actually account for this randomness, we need to use some statistical tests. We're going to run both algorithms multiple times, and we're going to be using statistical tests. First, we use the Wilcoxon signed rank test, which will determine the significance of the results. And then we will also use the Varga-Delaney A effect size, which is able to determine stochastic superiority between these two groups of measurements when they're run on the same metric, right? So if we run AutoRepair with the number of failing test cases, and we run Ariel on the number of failing test cases, we can use the Varga-Delaney effect size to actually determine stochastic superiority between these two different algorithms. And so that's how we're gonna actually measure and answer this this research question. And that brings us to the last slide of my presentation, where I'll talk about the future work that I will have to do for finishing my thesis. So first, I'll implement the hidden Markov model and the Viterbi algorithm, so I can actually do the first case study that I talked about. Then I want to actually run both of the experiments that are described in the case studies. Then I'll analyze the results and finish with writing the remaining chapters of my thesis, which would be the introduction, the background, approach, results, and the conclusions. And I would like to thank you for listening.